Yes.
Okay.
Okay. Again, 3 p.m. CET. Welcome to NLA. I'm Min Hong Chen. Today, Catherine will manage questions on Zoom. Hi, Catherine.
Hi.
And Jemima will manage questions on YouTube. Hi, Jemima.
Hi, Min Hong.
Okay. Now it's my pleasure to introduce today's speakers. Our first speaker is Elizabeth Newman. She is a postdoctor. Now she is a assistant professor in scientific computing from Emory University. The title of her presentation is Chain-like variable project, efficient training of neural networks with variable projection. Elizabeth, now it's your time. Please go ahead.
Thank you so much for the introduction. Let me just share my screen. And hopefully this works like it did before.
Yeah.
So can we all see that screen? And yell if you can't see it. But thank you very much for the introduction. I'm very excited to be here to talk about our recent work called Train Like a VarPro. This is a joint work with my advisor at Emory, Lars Ruthato, and our wonderful collaborators at Sandia National Laboratories, Joseph Hart and Bart van Bloemen-Wanders. So let's get started with a very shallow look at deep neural networks. And I'll start by saying breaking neural networks into these two big tasks that you sometimes see. The first one is classification, where you have, let's say, some image of a dog. This is my family dog's Honey, and we're trying to classify this image as a dog. So we put this image into a neural network, which we can visualize as a sequence of connected layers, and these connections are weighted, and we're trying to learn the weights that will give us this correct label. The other option is something like function approximation, where you have some true function, and as you train, your approximation from your neural network gets better and better, and the error goes down. There are many more tasks that you can do with neural networks, but these are the two broad ones that I want to focus on today. So the hype with neural networks, you've probably heard that they're universal approximators. They can be efficient surrogates, and they offer a flexible framework. But there are challenges associated with neural networks. They tend not to generalize well just if you train naively. They might overfit the training data. They're not interpretable. They're often this black box that is hard to understand. And training takes a long time. It can be incredibly inefficient. So we're going to focus on how we're going to improve the training in this talk. We're going to employ second order methods, try to introduce ways of potentially using more data parallelism. And kind of the heart of VarPro is we're going to find a way to choose optimal parameters as we train. So let's kind of let's talk about what does this mean, figuring out these optimal parameters. So in general, we have some set of inputs, Y. We want to find a DNN, a deep neural network, that maps to some true targets, C. And that's as abstract as I can make it. If you look at some of these state-of-the-art networks, they all look a little bit different. Their layers look different, but they have something in common. In particular, they have this separable structure. So their final layer can be written as just some matrix, some dense matrix applied to the outputs. So we're going to think about DNNs as having this separable structure. We're going to map from inputs to outputs with some nonlinear mapping F, parameterized by theta. So that's what we'll call the feature extractor, inputs to outputs. And then we'll separate this and have a final affine mapping, which I'll call a linear classifier. This doesn't have to be used for classification tasks only. It's just an easier way to talk about it. So with this separable structure, we can get a lot more bang for our buck by actually taking this into account. So let's do a quick kind of toy example to motivate why this is so powerful to think about this separable structure. Let's say we have some training data. So these are points on the plane, and they're classified as either the red or the blue class based on their distance from the origin. And if we run this through a neural network, the points, we can visualize them as moving in space. You'll see the points here. These are the dots here are the outputs Z. And our goal is to actually draw a line, a hyperplane between these two colors. That means we can classify them accurately. This black line is that line that classifies blue and red as the best it possibly can. And that's our W there. So getting the points into this new configuration, that's the feature extraction. And then drawing this line is the classification step. So there are two ways we can actually figure out this line. One is we can actually think about the W and the theta as being the same set, a big set of parameters in your network that you train with some network optimization strategy like stochastic gradient descent. So that's when we learn this W. The other way we can think about it is as we're training, why don't we just find the optimal W at each training epoch or iteration? And I'm going to give you two videos side by side to compare this. On the left, you're going to see the traditional treating W as a parameter that you learn. On the right, you're going to see what happens if we have W choose it optimally at each training iteration. So let's see if this works. So you can see here, it looks really good in the optimal case. The red and the blue, we can divide them perfectly. In this learn W case, it actually didn't do a great job. It definitely separated the red and the blue, but it didn't learn as well nor as efficiently. So let me do it one more time, because look how quickly we can learn if we use the optimal W. Right about here, we already have a good classification. So this is kind of the main idea of VarPro is, can we accelerate learning and do it better by using this optimal linear transformation or affine mapping at the end? So to put a little notation to this, let's say we have some training data set T, and we have our network weights that we're learning both here, W and theta. We want to minimize this objective function phi, and that's a combination of some loss function that measures the approximation of the target to the true target. This is our separable structure that you saw before, and some regularization as well. The main idea of VarPro is to eliminate this W and exploit this inherent coupling between theta and W, and this should accelerate the convergence as we saw in the previous example. So this leads us to the reduced objective function. phi red, which is just the full objective function above, but evaluated at this specific choice of W theta. And this W theta comes from a bi-level optimization strategy where we actually minimize the full objective function with respect to W only. And that's it. That's the whole idea of VarPro. Now, there's an important consideration here that we recommend in our paper to use a sample average approximation when you're training, meaning use large batches as opposed to small batches you typically see in stochastic approximation. And this avoids overfitting when you solve this inner optimization problem. We're not saying one method is better than the other, but for VarPro, we recommend using this SAA method. So now, we can avoid overfitting, but there's actually, I want to show you why you're going to love VarPro and want to use it yourself. Because there's some really nice property between VarPro and not using VarPro. And that is that the gradient of the full objective function with respect to W evaluated at that optimal W is equal to 0. And that leads to this nice property that the gradient of the reduced objective function with respect to theta is equal to the gradient of the full objective function with respect to theta, again, evaluated at this optimal W. So this means whatever you have already to train your neural network, you can do this and you can still just use VarPro. You don't have to change your gradient calculations or anything as long as you just need these gradients. So it's actually not too difficult of a change to make. So let's, the key here is we have to make sure we solve this inner optimization problem well so that the gradient is close to 0. So that's what I'll talk about next. How do we solve this inner optimization problem? And for us, we're gonna, we first noticed some really nice properties about this inner optimization problem. It's modest in size and does not depend on the DNN architecture, or really doesn't depend on the feature extractor at all. So it's something we can completely separate from the forward propagation through that nonlinear part of the network. The negatives or the challenges associated with this is that for a general choice of objective function phi that has these properties, there's no closed form solution. So we need some sort of iterative solver. And we want to make sure we can solve efficiently to a high accuracy. We want to reduce the overhead of using VarPro. So we're going to use a Newton-Krylov trust region method. That's what we've implemented, where you have your current iterate Wj, and you're trying to update it in the direction delta W, where you form this delta W by minimizing a quadratic approximation about your current iterate Wj. So this is our quadratic approximation. It's a trust region method. So at our current iterate, we can only take a step within a certain radius, within a certain ball. And when we do this, this would be our trust region step. It's minimizing the quadratic model, but stays within the radius. Compare that to, say, a line search method, which will minimize the quadratic model and then change the length of the step. And we're going to make better progress toward this kidney-shaped functions minimum right around here with the trust region method. So we like this. It's a more reliable method we found in practice. And additionally, there's efficiency and accuracy we can add in here. When we minimize this quadratic model, we use a GMRes approach, and so we get this low rank approximation to the Hessian. This approximation we can actually use later in our network. I won't be talking about that, but it's in our paper. But it's something that we don't need to store a lot, and we can reuse it. So you get a lot of bang for your buck here. Additionally, because the problem is modest in size and it's the final layer of your network, we can use double precision and detach, don't use automatic, and not use automatic differentiation. So you don't have to do these things, but it can really reduce the cost of using VarPro, and can give you all the benefits of using it as well. So this is the VarPro method, but we wanted to go a little further. And we were wondering, can we actually speed up training the network parameters theta as well. So we propose GNvpr, a Gauss-Newton-Krylov VarPro method. And here's just the reduced optimization problem as a reminder. The idea of GNvpr is that using a second order method, we can accelerate convergence and still achieve a high accuracy by having the VarPro in there. However, there's a challenge associated with this, where we have to implement Jacobians very carefully. So let's just compare it to what we saw before. Now we're updating theta instead of W, but we're using the same kind of trust region approach. The difference is the Hessian here, we're going to approximate by a Jacobian transposed Jacobian. And this Jacobian right here, with respect to W theta and F theta, so the affine mapping and the nonlinear mapping, has to be computed carefully. Both, we require some implicit differentiation to capture this W theta accurately. And also, it's expensive to go through the nonlinear feature extractor. And it's expensive to compute the Jacobian as well, which is going backward. It can be thought of as going backward through the feature extractor as well. So we want to reduce the number of times we have to do that. But yeah, once we have all of that machinery working, we now have a second order method to train networks. And I want to show you what you can get for this. So here's our first example. This is an image segmentation problem, where our goal is we have some image here and we're trying to label each pixel. As in this Indian Pines example, each pixel corresponds to some material or crop from a bird's eye view of the Indian Pines area. The loss function we're using here is a cross entropy loss, so it's non-quadratic. There is no closed form solution. And so we really needed a reliable iterative solver, that trust region, Newton-Krylov trust region method, to use VarPro here. And this is something that is new in our paper. You don't see it, we haven't seen it yet for neural networks. So here are just some results by picture here. So here's the ground truth you just saw. In this first column, this is the full Gauss-Newton, no VarPro. And this is our prediction, and you can see the difference is probably more helpful, how we didn't do very well. We didn't get a lot of the pixels accurately classified. Here's an SGD approach without no VarPro again, because the batches are too small, but it does pretty well. And here are two VarPro approaches. Here's the GNvpr that I described before. And this these all do comparably well, but what's surprising is that GNvpr had the best test accuracy. So it actually generalized better than SGD for this experiment, which surprised us, but we were excited to hear that, or to see that. And we're not exactly sure why, but definitely using large batches helped. So we were able to train faster, and we were able to generalize as well, and we want to explore this more. So I said we train faster, so I want to give you a different example to show you how quickly we can train. And here is a PDE surrogate modeling example, where we have some PDE that's parameterized by Y, and we solve it and discretize it into some set of observables C. So again, we're always mapping Y to C in this notation. Our goal is to train this neural network as an efficient PDE, as an efficient mapping that avoids expensive PDE solves. Here we use a mean squared error, so we can actually use some old VarPro techniques to solve the inner optimization problem. But here's a plot of the convergence. So this is the loss, how well we fit the data. And you'll see with GNvpr, we get to a lower loss, actually 2 orders of magnitude lower than even SGD, and we do it faster. So this is something we're really excited to see: high accuracy, fast training, especially for these scientific applications where accuracy matters a lot. So to wrap it up, in our group, we like to jokingly call GNvpr the backslash of neural networks, for those familiar with MATLAB. Again, I'm not saying it is or isn't, it's just a fun thing for us to say. We've seen it accelerates training of DNNs. We can apply it to non-quadratic objective functions. It does not depend on that feature extractor. And because we're using SAA methods and Gauss-Newton, we can potentially parallelize this significantly. We want to apply GNvpr to more problems, image classification, other scientific applications, implemented in other frameworks like PyTorch. We're close to having that ready. And we want to see if we can extend this to a stochastic approximation scheme. And that's where we're headed. So thanks for listening. Please feel free to check out our paper and our code and become a DNN pro yourself. So thank you.
Thanks, Elizabeth. Thank you for your great talk. Catherine, is there any questions on Zoom?
There aren't any questions, but I have a question, if that's okay.
Yes.
I was wondering, maybe this is a bit general. Are you aware of how sensitive your method is to perturbations, say in the data or elsewhere throughout the algorithm?
We haven't actually looked at that yet, but that's a really good idea. I'll even write that down. It's a great idea.
Okay, cool.
Okay. Jemima, is there any questions on YouTube?
No, none on YouTube.
Okay. Thank you, Elizabeth. Thank you again.
Okay, I'll stop sharing. Thank you very much.
Yes. Okay. Let's turn to our next talk. Next speaker is Samuel Hatfield. Samuel is a scientist from Europe Center for Medium Range Weather Forecast. He will be speaking to us on constructing tangent, linear, and adjoint models through automatic differentiation of neural networks. Samuel, please take it over. It's your time.
Thanks for the introduction, Minhong. I'll just share my screen and please tell me if you can't see it. Okay, so the subject today is a little bit on the outskirts of numerical linear algebra, but perhaps has some relations to Elizabeth's talk, and that is taking advantage of the easy differentiability of neural networks to construct Jacobians, essentially. And the application for this I'm going to present today is in numerical weather prediction. So I'm going to dive right in and explain the context for this research, which is an algorithm known as data assimilation, or rather a class of algorithms known as data assimilation. And for those who are not familiar with this class of algorithms, it is essentially for synchronizing a model with the real world via observations. So one example is what we call 4D-VAR, which is the four-dimensional variational algorithm. This is the one that we actually use at the European Weather Centre. And the purpose of this algorithm is to construct a trajectory of our numerical model that minimizes the distance to certain observations across a window of time, say 12 hours. So these observations, they just come from, weather balloons, buoys, satellites, etc. But they don't cover the Earth comprehensively in space or time. And so in order to construct a trajectory, we have to blend these observations with a numerical model, essentially to fill in the gaps, the areas that we don't observe. So what we do is we define an objective function or cost function, which measures the least squared distance between a trajectory of our numerical model and these observations. And then we use some kind of gradient descent algorithm or Krylov subspace method to minimize this cost function, giving us a more accurate model trajectory. In this case, it's the red line. So in order to do this procedure, we require three forward operators, and I'm using the word forward operator here very loosely. So the first one is the obvious one, the nonlinear model. This is an atmospheric model that advances an atmospheric state from one time to the next. So we feed in an initial state, x0. This is simply a list, a concatenated list of all of the variables of the atmosphere, that's pressure, temperature, wind speed at every grid point over the globe. And it gives us the evolved state of the atmosphere over that time. So we require not just this non-linear model, but also what we call the tangent linear model, which is just jargon. It's nothing more than the Jacobian of the non-linear model evaluated about this non-linear trajectory. So the tangent linear model allows us to evolve in time a perturbation to an atmospheric model state. And I represented this here by delta x0 instead of x0. Now, of course, the equations that describe atmospheric flow are nonlinear, and so perturbations are not evolved in the same way that full model states are. So we require the Jacobian in order to do this. And if you imagine this linear model as a matrix applied to delta x0, then we can construct something else called the adjoint model, which is nothing more than its transpose. Of course, we only deal with real numbers in atmospheric modeling, and so the transpose and the adjoint are the same in this case. We just call it the adjoint for full generality. The adjoint model is quite a difficult thing to get your head around, but the best way to think of it is it allows you to propagate gradients of scalar functions backwards in time. So let's suppose our cost function is evaluated at a later time. This is j. It's just a scalar cost function that's a function of the variable. The adjoint model allows us to propagate that backwards to the beginning of the initial of the assimilation window. Now, to give you a bit more examples of these, how they're written mathematically, the nonlinear model is very simple. It's just an nonlinear operator m. We feed in x0 and it gives us xn, which is a time-evolved atmospheric model state. Tangent linear model looks similar. In this case, it's an upright linear operator evaluated about the nonlinear trajectory, which we, in this case, apply to a perturbation. And the adjoint model, as I said, is the transpose of this linear operator, and we use that for propagating gradient. And I've shown here some pseudocode, which looks like Python. You don't need to concentrate on this too hard. It's just if you're curious how these different models are actually implemented in practice. So these three models have to be consistent with each other. They have to satisfy certain criteria in order for data assimilation to actually work correctly. One of those I've shown here. This is actually the definition of the adjoint model with respect to the tangent linear model, where delta x and delta y are just arbitrary small perturbation vectors. So once we've constructed these models, once we've written the code, we have to check whether they satisfy these criteria before we really use them to do any data assimilation. Now, I'd like to talk a bit more about how atmospheric models themselves are constructed. So this is kind of a crash course in numerical weather prediction. We like to say that atmospheric models can be decomposed into two components. They're what we call the dynamics and what we call the physics. So the dynamics, you can think of that as the resolved fluid flow of the atmosphere. So we essentially use a cut down version of the Navier-Stokes equation to model the weather. And so we have to discretize the entire atmosphere into grid boxes across the whole globe. And anything smaller than the grid box size will not be resolved. So the resolved flow we call the dynamics, and the unresolved flow we call the physics, which is quite a stupid label, to be honest, but that's what we call it. The full name being physical parametrisations of unresolved processes. I've given a couple of examples here. For example, convective clouds or cumulus clouds, the ones you might see on a sunny June day over a field. These are, by our perspective, very large, but according to the atmospheric model, they're actually quite small. The highest resolution model we use at the European Weather Centre is only 9 kilometers resolution. And so these clouds are actually too small to be represented. So instead, we parameterize their effects on the resolved flow in a statistical way, and we call this a parameterization. Another example I've shown here is gravity wave drag. This is the one I'm actually going to focus on today, and I'll explain that later on. So in order to construct the tangent linear and adjoint models of a full atmospheric model, we have to do it for the dynamics and the physics. And generally speaking, writing tangent linear adjoint code for dynamics is actually quite easy, but for physics, it's generally very difficult because those physics subroutines, they tend to be very esoteric. They're written by a domain specialist, someone who is really good at understanding clouds and not much else. So the code itself is often quite difficult to process. But also physical parameterizations often involve sharp nonlinear processes. For example, you click your fingers and a cloud appears. There are many if statements and step functions which are difficult to linearize. And so constructing the tangent linear and adjoint models of physics subroutines is hard. And so we want to find any way that we can to help this process. So what I'm going to propose today is quite a simple idea. what we're going to do is train a neural network to act as a surrogate for an existing physical parameterization subroutine. So it's going to be a drop-in replacement for just a Fortran subroutine that hooks up with the rest of the code nicely. Then, instead of coding the tangent linear and adjoint models of the original physics scheme, which, as I said, is quite difficult, we're going to do that for the neural network, which is trivial. And that's because neural networks are, by design, easily differentiable. And they have to be in order to train them through backpropagation. Then I propose to do data assimilation with these tangent linear adjoint models based on the neural networks instead of based on the original linearized physics code. So I can think of a couple of advantages to this. Really, I'm doing it out of curiosity, but the code will be much more compact than the original code. Tangent linear adjoint code is notoriously messy and difficult to read. But the neural network code that I've already written is quite compact, and we only have to write it once. So in principle, we can reuse this neural network code for many different physical parameterizations, not just the one that I'm focusing on today. And secondly, the neural network evaluation itself is really nothing more than a bunch of matrix-matrix multiplications evaluated at every grid point. And this is exactly the kind of operation that you could outsource to an accelerator like a GPU. So in principle, it could actually accelerate the code. So the physics scheme I've chosen is something called nonorographic gravity wave drag. This is gravity waves. That's nothing to do with these relativistic gravity waves. It's simply a coincidence of terminology. And what the scheme describes is how waves, density waves, which are triggered in the troposphere at the bottom of the atmosphere, propagate up to the top of the atmosphere where they break, just like how the waves on a shore might break, where they deposit momentum, essentially acting as a drag force on the wind there. And so the input to this physical parameterization routine is a column of atmospheric variables. So there's no consideration of the horizontal, it's all vertical. And the output is a column of wind tendencies at that same co-located point. So we're basically modeling the drag due to these breaking waves. And I'm going to be testing this idea inside our state-of-the-art atmospheric model, which we call the Integrated Forecasting System, or IFS. And the chosen neural network architecture is deliberately simple and bog standard, as they say. It will simply be a fully connected multi-layer perceptron with hyperbolic tangent activation functions. So this is really nothing state-of-the-art, none of this ReLU activation or convolutional layers or anything like that. I wanted to keep the code as simple as possible so that I could differentiate it easily. And I won't talk about the training methods. Suffice it to say that we successfully trained a good surrogate for the existing subroutine. Okay, so before we test this idea in the full atmospheric model, I want to show to you that it does pass the tangent linear adjoint tests that I mentioned earlier. The first one, which I've already mentioned, is to check whether these two expressions are the same. Now, because in reality, this M applied to delta X is actually a Fortran subroutine, it's using floating point arithmetic. And so we shouldn't expect these two to be exactly the same, but rather to be similar to at least the machine epsilon. So the left-hand side and the right-hand side, the normalized difference should be around 0 with 16 decimal places, followed by 1. And suffice it to say that the test does pass in this case. I've tested this on my hand-coded neural network linear code, and it works. The second test is to test whether the tangent linear model is a good linearization of the nonlinear model. So we're essentially checking the size of the second term or the first term, if you count it from 0, of a Taylor expansion. So we want this epsilon to be as small as possible. Now, in reality, it won't actually be completely 0, even if M is perfectly coded, because the atmosphere does not, it's not a linear system. Errors grow non-linearly. But we at least want epsilon to match the epsilon from the existing state-of-the-art code. So that's what I'm showing here for 3 variables: temperature, zonal wind, and meridional wind. That's eastward wind and northward wind. I'm showing as a function on the y-axis of the model level. So this is the bottom of the atmosphere and this is the top. I'm showing you the relative change in epsilon when we use neural networks instead of the state-of-the-art code. And in this case, this is a relative error. So you can see that epsilon is actually below 0 for most of the atmosphere, which means that when we use neural networks, our tangent linear models are actually better approximations to the nonlinear model than they were before, which is, I think, quite surprising. And so I've actually put this back into our real atmospheric model and used it to perform weather forecast tests with data assimilation. And the take home from this figure is that the neural network gives essentially no change in the forecast scores. So what we're seeing on the right here is an error, a temperature error difference between two experiments. So we want this to be 0, or at least 0 or negative. We don't want it to be positive. And we're showing it for a few different lead times going into the future. So starting with 12 hours, going up to 5 days, that's t plus 120. So you can see a lot of blotches here. It's not exactly white, but suffice it to say, our algorithm does add hatching when there is statistical significance. And in this case, there's basically none. So this noise here is not statistically significant. In other words, when we use a neural network, we see no change in the forecasting error. So in principle, if we were to put this back into our operational system, we could use it to do actual weather forecasting and we wouldn't see any degradation. Now, a few further experiments I'd like to try. I mentioned that there could be computational savings because of the simplicity of the neural network evaluation, but actually the neural network code is about the same speed as the existing one, if not slower. It's very hard to beat systems that have been optimized in an operational setting for 10 or 20 years. So as I said, maybe it's worth trying it on a GPU. So you could imagine outsourcing the evaluation of this neural network to a GPU, and that should be much faster. Secondly, there might be a possibility here to actually improve the weather forecast skill by training the neural network on a more physically realistic parameterization instead of the one that I did here. And the neural network is the same cost regardless of how accurate it is a surrogate for reality. So we can find a way to improve the realism of the neural network by training it on a more complex but expensive scheme. We might actually be able to improve the forecast scores. So that's basically, I'm going to finish there and say that neural networks can be differentiated trivially by design. And so they're the ideal building blocks for these Jacobians, tangent linear and adjoint models, which are essential to doing 4D VAR data assimilation. I've done some preliminary tests with a specific physical parameterization scheme. And I found that, well, I would say they were successful because there was no degradation in the skill of the weather forecasts. But it's very difficult to match the computational performance of the existing Fortran. And so getting there will require some more effort. So thank you for listening.
Thank you, Samuel, for your wonderful speech. Catherine, is there any questions on Zoom?
There aren't, but I will again ask a question just so that the speakers have questions. I was curious if, I guess you touched on this a bit by measuring degradation, but since you're replacing physical properties by very simple neural networks, essentially, are you concerned that you're not approximating the correct thing physically? Or does that not seem to show up?
Well, we've compared the subroutine that we're trying to emulate with our emulation offline. So we've just compared the numbers to see if they give the same outputs from the same inputs. And that is pretty much the case. So we're confident that our surrogate is a pretty good surrogate for the existing subroutine. Yeah.
When you say compare the numbers, are they up to what order of accuracy? Are they the same?
Oh, I don't know the numbers off the top of my head.
Okay.
But we've tried quite a few different architectures and training schemes.
Okay.
We've tried many different things. It's not a perfect surrogate, but that doesn't seem to be resulting in degraded weather forecast skill in this case.
Cool.
Okay. Jemima, is there any questions on YouTube?
No, but I have some questions. So one of the annoying things about adjoint code is that if you make a change to your model, you have to go and change your adjoint, which can be really difficult, right? So what, in terms of the neural network, you could just rerun it if you had like a big code change to your model, but could you actually, do you think there's a way to reuse the existing neural net to make that process?
Yeah, so in this case, the nonlinear, the tangent linear, and the adjoint all share the same hyperparameters. And so if there's a modification to the nonlinear code, all you have to do, and well, of course, this is not quite as trivial as I'm presenting it, but all you have to do is retrain the nonlinear neural network, and you can then reuse those same hyperparameters in the tangent linear and the adjoint model automatically. The actual code doesn't have to change.
Okay.
So in principle, this technique could save a lot of manual labor. You know, at the European Centre, we actually have 2 full-time staff just for managing the tangent linear and adjoint models. So they're quite nasty things to deal with.
Great, thanks.
Okay. Thank you again for our two speakers' great talk.
Thanks.
And I should share. Now, next week, we will also have 2 talks. Next week, we also have 2 talks, and now we are considering about the future of NLA, and you should have received the survey from the survey form from Google Group, and your feedbacks will be important to us, and we would be thankful for your feedbacks. And thank you all for your attention, and we hope to see you later on the other. Bye.